In this video, you will learn both how a stepper motor works and how to control it using Python code. You should already be able to control an LED using a GPIO output pin, be familiar with arrays, and be able to use for loops. First, the specifications. We will be looking at the 28BYJ48 stepper motor. Stepper motors vary in design, though they all share one quality. They rotate by taking a fixed number of steps. This is in contrast to a regular motor, which simply spins when powered on. This means a stepper motor can be used when a rotation by a certain angle is needed. The input voltage is 5 volts, which we can power from the Raspberry Pi's 5-volt rail. One revolution requires 32 steps. That means 16 steps would rotate the motor by 180 degrees, halfway around. For greater resolution, the size of the steps are reduced by a factor of 64 using gears inside the motor's housing. Taking these gears into account, internally the motor actually needs to take 2,048 steps for one revolution. This is for full stepping. For half stepping, the resolution is doubled to 4,096 steps. Later in this lesson, we'll go over the difference between full and half stepping. Let's take a moment to look inside the stepper motor. I've already bent back the metal in these 4 places, so it should be relatively easy to pull off the outer metal cap, which reveals the gear assembly inside. We saw in the specification that these gears provide a 1/64th reduction. What that means is if I want this part, the part that comes out of the stepper motor, to spin one full revolution, I need the center part to spin around 64 times. Now let's remove the gear assembly, which exposes the core, so I'll take that out. And the core is really several magnets. If you rub something magnetic such as iron against the core, you'll feel the attraction, but you'll also feel some bumpiness. Specifically, you'll feel 16 bumps. You'll feel 8 north poles and 8 south poles. Next, let's pull out the coils. Notice at the bottom we see a set of 8 teeth. Looking back at the coil, if I take off the first plate, then I also find 8 more teeth. And also, if I look inside the coil, I see 2 more sets of 8 teeth. So in total there are 32 teeth, and that's why I stated in the specifications that there are 32 steps in one revolution, 1 step for each tooth. Now let's discuss how this all works when put together. To understand how the stepper motor works, there are a few important elements to be aware of. Between the core and the coils are 4 levels of 8 teeth. Each of these teeth can be magnetized to act like tiny north or tiny south magnetic poles. The next thing to note is the core itself is made up of 16 magnetic poles, 8 south poles and 8 north poles. Because the teeth can be magnetized, the teeth can pull on the magnets in the core and cause the core to rotate. So how are the teeth magnetized? Well, when a coil has an electric current running through it, it will produce a magnetic field, either upwards or downwards. If the current is in the counterclockwise sense, the field is upwards, with north pointing up and south pointing down. On the other hand, if the current is clockwise, the magnetic field is pointing downwards, with north pointing down and south pointing up. For instance, if the top coil has a counterclockwise current in it, north would be pointing upwards, making the top teeth north poles and the bottom teeth south poles. This diagram shows the teeth a little bit more clearly. Remember that in total there are 16 magnetic poles on the core, but right now let's just keep track of one of the north poles, which we can represent by a red bar. When the first coil is energized, the north on the core will move to a south pole, and this is the first step. Then the top coil is switched off and the bottom coil is switched on so that the bottom teeth become north poles. This will cause the pole to shift towards the closest south, rotating the core a small amount. This is the second step. Next, the top coil is switched on again, but with south poles on the top teeth, causing the pole to move a little bit more. This is the third step. Lastly, the bottom coil is powered with south poles on the bottom teeth, causing the pole to move a little more, as the fourth step. Which finally brings us back to the first step, and then the cycle continues. So there are 4 steps for each cycle, which makes sense as there are 4 sets of teeth, a pair for each coil. And since 32 steps are needed for 1 revolution of the core, that means that there are 8 cycles taking place. Let's look at another way we can represent stepping. We have 2 coils, here represented by the orange rings and the green rings. In 2 cases, the field was directed with north pointing upwards, and in the other two cases, north is pointing downwards. We can represent this using arrows, but the main point to outline is that there are only 4 separate steps. The red arrow in the middle shows which step we are currently at. The motion we have so far discussed is known as single-phase stepping. If we go through one cycle, we go through each of the 4 steps, and then repeat. We can put this information into a table, using 1 to represent on and 0 to represent off. The first step has only one coil on, with north pointing upwards. The second step only has coil 2 on, with north pointing downwards, and so on. This works, but we can do better than this. Let's consider having 2 coils on at the same time. This is known as dual phase stepping. Notice we still have 4 separate steps, but this time 2 coils are moving the core. This will require twice the electrical current, but will result in a greater turning force. This process is also known as full stepping. Each of the 4 steps is outlined in this table. As we have an added turning force, this is an improvement over single phase stepping, but we can still do better. A third method is known as half stepping. It's really a combination of single and dual phase stepping. It alternates between 1 coil and 2 coils being turned on. In half stepping, 1 cycle takes 8 steps, thus doubling the resolution of the stepper motor. The downside is that the turning force is about 70% to that of full stepping. Also, it would appear to be twice as slow as full stepping, but in practice you can usually make the core spin more quickly in half stepping because the core will be more responsive to each step. We must now figure out how to program each of the 8 steps. First off, there are 4 pins on the motor's control board, so we need only set 4 output pins as either high or low. Next, we can think of one step as a 4-element array, which itself is an element of an 8-element array. To start our program, we first import the relevant modules and set how to reference the pins. We will need the time module to add a delay between turning on and off the control pins. Next, we make an array listing the GPIO pins which we will use to control the motor. We set each as an output pin and then each to low. The 2-dimensional array sec holds the 8-step sequence for half stepping. If you're interested, you may want to make another array for full stepping so that you can compare it to half stepping. This for loop will be used to cycle through the sequence a given number of times. Here I've chosen 512 times, as that will result in a full revolution. Recall that inside the motor, 8 cycles correspond to 1 revolution of the core, but as it is geared down by a factor of 64, that gives 512 cycles for 1 revolution. We have 8 half steps, so we need a for loop to go through each of them. And we also have 4 pins to loop through. Notice that I've added a time delay outside the for loop. This means that the pins are first all set, and then there is a pause in the program. Without this delay, the coils would be turned on and off at a rate too fast for the magnetic core to respond, which would result in no rotation. Lastly, let's look at how we set the output of the control pins. Let's take for an example, half step equal to 0 and pin equal to 0. Half step equal to 0 corresponds to this element in the sequence, and pin equals 0 corresponds to pin 7. So our output line would tell pin 7 to set itself equal to row 0 at position 0, which is equal to 1. 1 corresponds to on, so pin 7 would be set high. The for loop would then move on to the next pin, which in this case would be pin 11, and set it to low. Once these 4 pins have been set, there would be a delay, and the for loop would move on to the next half step. Lastly, we should include a cleanup command so that all of our pins are reset once the program ends. For my setup, I really have a ridiculous number of wires. You really shouldn't need to use even a breadboard at all if you have female-to-female jumper wires. I don't, so all I've done here is I've taken one of these wires, say one of my output pins, the yellow one here, I've put to the breadboard, and then I've continued that towards the control board for the motor. Okay, let's give the program a run. And there I've attached a clip onto the motor so that we can see that it makes 1 full revolution. Now you probably also noticed that there were 4 LEDs here that turned on as well when that was turning. Well, those LEDs represent which of the outputs are being turned on and off, which are being raised high and which are being raised low. So if I slow down my program, we can actually see them slowly blink through and do that half-step motion. So if you're having some trouble with your program, that's a good way of starting to debug things, is to look through those LEDs and see if there's any problem there. Okay, well, I hope you give this a try.